All right, good morning, everybody. Nobody is in the meeting yet, so I'm going to go ahead and get started on the examples that I prepared for today. And then if anybody joins me, I will add them to the participation of these examples. So I'm going to go ahead and start here. So what we want to do is determine how many HNMR signals will be in each of these molecules. Okay. The first thing you need to look for is if there is a stereocenter in the molecule. If there is a stereocenter, then all of your CH2s show two signals, two distinct signals. So just watch out for that. So you need to first determine if a molecule has a stereocenter. If it does, then you will have your CH2s show up as two different signals in your HNMR. Okay, so for looking at this first molecule, there is a stereocenter here, okay, because we've got a hydrogen, an OH, and two different carbon groups, all right? So we do have a stereocenter. So that means we need to go through and label all of our different hydrogens. So we've got our HAs here, HB, HC, HD, HE. Because these are both CH2s, that's why these are different peaks here, okay? And then this hydrogen will be HF, this hydrogen G, HH, and these two will be separate as well. So HI and HJ. So we have a total of 10 HNMR signals. Okay. Let's go on to this next one. Again, we need to look to see if there's a stereocenter. I do not see one in this molecule, so we can go ahead and just start labeling our hydrogens. HA, HB, HC, HD, HE. Okay, so for this one, we're going to get 5 signals. All right, moving on to this next one. There are no stereocenters in this molecule, so we'll go ahead and just draw all of our hydrogens. And there is no distinguishing factor between any of these hydrogens, so there's only going to be one HNMR signal. There's no functional groups, no substituents that would cause any of these to be different from one another. All right, this next molecule, no stereocenter. We do have this functional group right here, and if you were to draw that out, it would be a carboxylic acid. Okay, so that's what that group looks like all drawn out. So we have HA, our two HBs, HC, HD. So we have 4 signals. Going on to number 5 here. We need to look for a stereocenter, and yes, there is a stereocenter here because we have a hidden hydrogen. Okay, we have 4 different groups around that carbon. So our CH2s will show as different peaks. So let's go ahead and draw all of our different hydrogens. These will all be HA. This will be HB, HC, HD, HE, HF, and these 3 will all be HG. So a total of 7 signals. for this example. All right, moving on to this next one. So we do have a potential stereocenter here, but these two carbon groups are identical to each other. And there's also a plane of symmetry, okay? So there's no stereocenter. Our CH2s will show as one peak each. So we can start here with HA, HB, and these will also be HBs because they're identical to the others. And these will be HC, and these will also be HC because they're identical to each other. Okay. So here we've got, these are identical to the opposite side. Same with our HBs. Moving on to the next ones. All right, so no stereocenter here. So we've got HA, no hidden hydrogen here. We do have a hydrogen here, that'll be our HB. And then these two are identical to each other. Okay, so these are both going to be HC. So we get 3 signals. All right, carrying on to the next one, no stereocenter here either. But on either side of a double bond, we always have separate hydrogens. So this is HA and HB. All 9 of these at the end here, because we have 3 hydrogens per carbon. All 9 of these are going to be identical to each other. So this will be our HCs. No stereocenter, so this is HD and HE. 5 signals. All right, on this next one, we do have a plane of symmetry. Okay. And we do not have any stereocenters. So that means anything we do on one side is identical on the other. So we have HA. These two are identical to each other, HBs. And over here, this is also HA, and those two are HB. Again, we've got HAs are identical, HBs are identical. All right. We need to look for stereocenter. And in this case, yes, we do have a stereocenter right here. Okay. So all of our CH2s will show as separate signals. So here's our only CH2, so we'll call this HA and HB, HC, HDs. Those are all 3 of those are HDs, and the 3 down here will be HE. So we have 5 signals. All right. We need to look for stereocenter, and this molecule does not have one. So this will be our HA, HB, HC, and HD. Okay, so we're going to have a total of 4 signals. This molecule. All right, last 2 examples for finding total number of signals. Rings are treated a little bit differently. You kind of have to look at this as a whole separate molecule. Okay, so what we're going to want to do is kind of draw it in a 3D way where we can kind of look down the bonds. Okay, so each of these carbons is going to have something going above it and something going below it in a ring, right? So we can start here. This is our chlorine. Okay, and so below it we have a hidden hydrogen. And then the rest of these are going to be hydrogens as well. Okay. Because it's a ring structure, there's something going above it and something going below it. And so we can draw all of those hidden hydrogens in. Now we want to determine the difference between each of these. So the hydrogen attached to the same carbon as the chlorine is going to be separate from all of the rest of them. So we'll start there with our HA. Now we're going to determine the difference between this one and this one. Okay. If you look at these, you can tell that they're kind of in the same plane, right? They kind of have the same atoms influencing them. They are near the chlorine. They're both facing up on the same direction as the chlorine. They have no other electronegative atoms pulling on them, making any difference for them. And so these are going to be identical to each other. So these are our HBs. Then we'll go to the bottom carbons. And again, those are going to be different from our A and B. Okay. So those will both be HCs because they're in a different plane from anything else we've looked at. Okay. We'll go to the top carbons here, or top hydrogens, I apologize. And we'll look at the difference here, okay? So again, they're kind of in the same proximity to the chlorine. They're both facing up in the same direction as the chlorine. No other electronegative atoms pulling on them. So we're gonna have these be the same as well. So those will be HDs. And the hydrogens down here will be different from all the rest of them. So these will be HEs. So we have a total of 5 signals for this one. We have A, B, C, D, and E. Okay. So now we're going to do the same thing for this next ring structure. We're going to kind of draw it in a 3D way so that we can see each of these bonds. Okay. So we have a 4-member ring. We have a bromine facing downward, and the rest of them are hydrogens. Okay. So the hydrogen attached to the same carbon as the bromine is going to be unique to the rest. These 2 hydrogens at the top are in the same field as each other, so these are going to be our HBs. Down here are our HCs because they're facing the bromine. And then HD up here and HE down here. So again, another 5 signals total for this 4-member ring. Okay. So now we need to actually apply our knowledge about taking a chemical formula and an HNMR graph and drawing a structure from those 2 bits of information. Okay, and these numbers I've drawn on here are integral values, which means that this tells us our ratios of how many hydrogens there are to each other. So the way to solve these is to take your integral value. Okay, so we'll take our first one here and we divide it by our lowest integral value, which in this case is the 22.7. Okay, we're going to do that for all of them. So we have our 37.2 divided by the lowest, which is 22.7. We also have 36 divided by 22.7. Now if you do this, this comes out to 1. This comes out to about 1.6. And this comes out to about 1.6 as well. Okay. So now we know that the ratio on these is 1 to 1.5 to 1.5, just about, okay? 1.6 is close enough to 1.5 that we can just round it, okay? But we don't want our ratios to be partial numbers. We want them to be whole numbers, okay? So we're going to multiply all of these by 2, which will give us a ratio of 2 to 3 to 3. So now we know that our ratio for our molecule is going to be 2 to 3 to 3. Okay. So now we want to determine how many hydrogens are going to be in each of these peaks. Sorry, how many neighbors they're going to have. We've already determined how many hydrogens. We want to determine how many neighbors. Okay. So when you see a peak, right here we have 4 peaks. Right? Right here we have 4 peaks. When you see 4 peaks, you know that those hydrogens have 4 minus 1 neighbors. It's the n minus 1 rule, okay? So when you're looking at the number of peaks, you take the number of peaks minus 1, and that gives you how many neighbors they have. So let's just go ahead and write 3 neighbors here. Okay. This peak only has one long, strong peak. Okay. So n minus 1 gives us 0. So this one has 0 neighbors. Okay. And we also look at these peaks down here. 3 peaks gives us 2 neighbors. Okay. So now we know that we have 4 carbons, 8 hydrogens, and an oxygen. We know that each of these peaks represents a certain number of hydrogens. We also know how many neighbors each of these peaks have. And in order to be a neighbor, they have to be within 3 sigma bonds, and I'll explain what that means in just a minute. Okay. So first I'm going to just start with a 4-carbon chain. That's usually how I like to handle these. So now we have 4-carbon chain, and we can edit as we go along just to kind of change what we're doing here. We also have an oxygen to add. Okay. We could either try drawing an alcohol group, or we could draw a ketone, we could draw an aldehyde, okay? But you're gonna want to determine what's gonna be the best in order to have our number of peaks and also how many neighbors each of those peaks have. So I'm gonna just guess, and I'm gonna say we have a ketone, okay? So I'm gonna put the ketone right here. So now we wanna look at if we have our correct chemical formula, if there's 8 hydrogens, 4 carbons, and 1 oxygen. So let's double check that. We have 3 hydrogens here, 2 here, and 3 here. That does give us a total of 8 hydrogens. So we do have a correct chemical formula, but let's make sure that it matches our HNMR graph. Okay, so we need to look for, okay, we know that there's, in this middle peak, there's 3 hydrogens with 0 neighbors. So we need to look for anywhere in this molecule that there would be 3 hydrogens with 0 neighbors. And if you look closely, that would be this CH3 right here. Okay, we have these 3 hydrogens that are not within 3 sigma bonds of another hydrogen. Okay, so that does fulfill that requirement. Okay. So now we're going to look for 2 hydrogens that have 3 neighbors. Okay, so here's the only place that there's 2 hydrogens in this molecule. Okay. And if you look closely, there are 2 hydrogens here, and they do have these 3 neighbors on the end. So we have hydrogen, carbon, hydrogen bond. That's within 3 sigma bonds. Okay, 3 bonds away are our neighbors. So that does check out as well, that we have 2 hydrogens and 3 neighbors. Okay, so let's double check here. Here we know we have 3 hydrogens with 2 neighbors, and that's where we see this group, 3 hydrogens with these 2 neighbors. We already knew that they were neighbors, okay? So this molecule does check out, and this is our structure based on the HNMR graph. Again, if you went through this and you decided, well, let me try it with an alcohol, okay? You would see that here's our 4-carbon chain, here's our alcohol. First of all, you'd have too many hydrogens, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, too many hydrogens, but you could also add a, you know, something like this. 1, 2, 3, 4, 5, 6, 7, still too many hydrogens. So that wouldn't have worked out, okay? And then if you tried to add an aldehyde, here's our 4 carbons and our aldehyde. 8, okay? You'd have 8 hydrogens, 4 carbons, and an oxygen. That does match our chemical formula, but it does not match our HNMR because there would be 4 different signals in this molecule. We'd have HA, HB, HC, and HD. Whereas in our HNMR, we only had 3 signals, okay? So that's how you know that it's not an aldehyde. All right. So you got to go through and make sure that everything all checks out before you move on, okay? So there's our answer right there. Okay. By the way, you could have had the ketone here as well. It doesn't matter, it's the identical molecule. Okay. All right, same process again. So we've got our chemical formula here, and we have 3 HNMR signals and the integral values. So first we want to find how many hydrogens, what our ratio is, how many hydrogens are in each of these peaks. So again, you have to do your 13.6 divided by the lowest number peak, lowest integral value, which is our 13.6. Okay, we're also going to divide 41.1 divided by 13.6 and our 82 divided by 13.6. Okay, so each of those we get roughly 1, roughly 3, and roughly 6. Okay, again, they're not perfect, but as long as they're close enough, it's going to tell you the integral value. So we know that our ratio is 1 to 3 to 6 for each of these signals. Okay. Now we need to look at how many neighbors these are all going to have. Okay. Let's start on the right side here. Okay, so we know this peak has 6 hydrogens. Okay. And we also know that because there's 2 peaks, we do our 2 minus 1 rule. N minus 1 gives us 1 neighbor. So 6 hydrogens with 1 neighbor. Here we know we have 3 hydrogens. 1 peak means that there are 0 neighbors. And then on this one, we have 7 peaks. I know it's really hard to see, but 7 peaks give us what's called a multiplet. Anything more than 6 peaks gives us a multiplet. And on your exam, Dr. Garg would tell you, hey, this is a multiplet. He'd let you know because they're usually hard to tell when the multiplets are, but this is a multiplet. So that means that there are 6 neighbors, okay, and 1 hydrogen. 1 hydrogen, 6 neighbors. Hope I didn't confuse anybody there. Okay, so let's start with our carbon chain. Okay, so again, we're going to look at 5 carbon chain, and I just like to start off with a 5 carbon chain. Okay, so there's our 5 carbon chain. We have an oxygen. Okay, I'm going to try a ketone. I don't know what it is yet, but we'll start with a ketone. Okay. So now we need to determine if it fulfills our chemical formula. Okay, so we have 3 hydrogens, 4, 5, 6, 7, 8, 9, 10. So yes, we do have C5H10O. Okay, that is a good chemical formula. We need to check if it fulfills our HNMR graph. So we have 3 hydrogens with 0 neighbors. Okay, so that does check out here. 3 hydrogens, 0 neighbors. All right, let's go on to the next one. Here we have 2 hydrogens, and it's going to have these 2 neighbors right here. So 2 hydrogens and 2 neighbors. But I don't see anywhere on this graph that there's 2 hydrogens with 2 neighbors. So we must have something wrong. So let's reevaluate here. Okay. So I know we're happy with the chemical formula with the number of hydrogens. So why don't we just take this carbon on the end off and turn it into an isopropyl group? Okay. Now I'm just playing around, trying a few things to see if we can make it work for us. Okay. I don't know if this is right yet or not, but we're going to go here again. We have the 3 hydrogens with 2 neighbors, or sorry, with 0 neighbors. And again, that does check out. Okay. We can look here. We have 1 hydrogen with all 6 of these neighbors. Oh, okay, so that does match as well. We have 1 hydrogen with 6 neighbors, 1 hydrogen with 6 neighbors. Now we can look at these hydrogens. We're going to have all 6 of these hydrogens are going to be the same. So we have 6 hydrogens. Let me draw it like this. We have all 6 of these, 6 hydrogens. And we have one neighbor. It's just that lonely hydrogen right down in there. Okay. So we have 6 hydrogens with one neighbor. And we can look at our HNMR and see if that comes out, and it does. Okay. So now we look through the whole thing. Okay, let's look at our overall molecule. We say it does fulfill our chemical formula, and each of our HNMR peaks are happy and fulfilled, and thus this is our structure. Okay. Now I know this is tough. It's kind of hard to look at this and be able to say, hey, you know, how am I going to be able to work this? What kind of functional groups can I use? But there are patterns that Dr. Gard does teach us to watch out for. Okay. And let me talk about one of those for just a minute. If you have an HNMR signal that has 6 hydrogens and one neighbor, and in the same HNMR graph you have a 1 hydrogen peak with 6 neighbors, those two together tell you you're going to have an isopropyl. Okay. Those two hints together, that's the only functional group, the only way that hydrogens and carbons can be together that will let you know that there is an isopropyl group. Okay, so watch out for that. If you have 6 hydrogens with one neighbor and 1 hydrogen with 6 neighbors, you know that you're going to have an isopropyl group. Sometimes this 1 hydrogen may have a few more neighbors, but again, it's a multiplet, okay? And Dr. Gard teaches about that in his lecture slides, but if you have a multiplet, you can also count that as a signification that you do have an isopropyl. So 6 hydrogens with 1 neighbor, 1 hydrogen with a multiplet tell you you have an isopropyl. Okay. All right, a little bit more of a few more peaks we have going on with this molecule. We have a C5H11O. All right. So again, we want to find our ratio. So we're going to do 6.3 divided by our lowest number, which is 3.1. We're going to do 9.2 divided by 3.1. We're going to do 3.1 divided by 3.1, 6.3 divided by 3.1, and 9.5 divided by 3.1. Again, this is going to take our integral values down to our number of hydrogens in these peaks. Okay, so 6.3 divided by 3.1 is about 2. 9.2 divided by 3.1 is about 3. This is 1. This is about 2, and this is about 3. Okay. So we know our ratios 2 to 3 to 1 to 2 to 3. Okay. Now, if all of these add up to 11, then we know this is our absolute value of hydrogens. So here we have 5, 6, 7, 8, 9, 10, 11. So yes, that does add up. So that's how we know that this is the exact value of hydrogens in each of these peaks. So we can go ahead and just write that right here. This has 2 hydrogens. This has 3 hydrogens. This has 1 hydrogen. This has 2 hydrogens. And this one has 3 hydrogens. Okay. So now we need to think of a structure that fulfills C5H11O. Again, I'm going to start with a 5-carbon chain. And we can go ahead and start with a ketone. Okay. Let's see if this fulfills our chemical formula. So we know we have 5 carbons and 1 oxygen. Let's see if there's 11 hydrogens. We have 3, 4, 5, 6, 7, 8, 9, 10. So not quite. Okay. So maybe we could turn this into an alcohol. Let's try that. So we know we have our 5 carbons, one oxygen. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Still too many hydrogens. Okay. So I'm going to try making an ester group an ether group. This is an ether group. Okay, you've got an oxygen in between two carbons. Okay, so let's see if this fulfills it. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, that doesn't quite fulfill it. Oh, you know what I forgot? I forgot that the chemical formula on this one, that's why I wasn't able to figure this out. We have a chlorine. Okay. Forgot to add that. Oh, Cl. We have a chlorine. So let's add our chlorine onto the end of our group. Okay, so we have a chlorine here. And then I was starting to try an ether group. Okay. So let's count our number of hydrogens. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So C5H11OCl. Okay, so that does fulfill it. Okay. Again, just keep playing around with it until you get something that fulfills your chemical formula, and then see if that matches your HNMR graph. Okay. So let's look at these 3 hydrogens right here. So we have 3 hydrogens and we have 0 neighbors. Okay, I forgot to write out number of neighbors in the graph, so let's go ahead and do that quickly. Here we have 3 peaks, so this is going to have 2 neighbors. 1 peak gives us 0 neighbors. This is a multiplet. Okay, and so we're going to have 1, 2, 3, 4, 5. That looks like 6. So I'm actually going to call that 5 neighbors. Okay, I'm not 100% on that one, but we'll look out for that. Okay, here we have 4 peaks. So we're going to have 3 neighbors. And here we have 3 hydrogens with 1 neighbor. Okay, we have 3 hydrogens with 0 neighbors. That does check out right here. Okay. Now let's look at this hydrogen right here. We've got 1 hydrogen. We have 3, 4, 5 neighbors. Okay, so we need to look for one of our peaks that has 1 hydrogen and 5 neighbors, and it looks like that does check out right here. So I was correct in saying that that had 6 peaks in that multiplet. Okay. You can tell there are 6 peaks there, and so that tells us there's 5 neighbors, so that checks out. Let's go on to these 3 hydrogens. So we have 3 hydrogens, and they have 1 neighbor. So again, we need to look for 3 hydrogens with 1 neighbor. And it looks like that checks out right here. Perfect. So we're looking good so far. We're going to keep going along here. We have these 2 hydrogens. Okay. And they have this neighbor, and they have these 2 neighbors right here. So there's 3 neighbors. So 2 hydrogens, 3 neighbors. Let's look for something in our graph that proves that. 3 hydrogens, 2 neighbors. Sorry, 2 hydrogens, 3 neighbors, which is right here. Perfect. And again, lastly, we have these 2 hydrogens. Okay, 2 hydrogens with 2 neighbors. Okay, because these are the neighbors right here for those hydrogens. So we got to check out and see if that's in our HNMR graph. And turns out, yes, it is. Okay. It's not a good color for that. Let's go This one. Yeah, that's better. Perfect. So all of our HNMR is fulfilled. All of our chemical formula checks out, and so we can erase all of this craziness. Apologize for all the crazy colors and everything, but I just wanted you to be able to visualize where everything was. So it does check out that this is our molecule. Okay. I can't imagine him giving you much more difficult than that. If he did, he would give you other graphs like your molecular weight graph. He'd give you your HNMR. He'd give you your all the other graphs that we've gone over to try to find the structures of molecules. So anyway, just be able to kind of do these, look at a structure, look at a chemical formula, HNMR, and be able to manipulate it in order to give you all of the peaks that show in your HNMR. And that was the end of what I prepared. So I hope that was helpful for everybody. Please feel free to reach out to me if you have any questions at all. I'll be happy to respond to you. The best way probably is through Canvas. You can message me directly through Canvas and I can answer any questions you all have. So feel free to reach out anytime you need to. Thank you all.